So today we're going to start our chapter 4, which is the continuous session from previous one. Just call it part 2. The objective that we have are going to be the same as the previous one, which we have. One is the stress strain curve, the second one is Hooke's law, third one the actual deformation, which we're going to talk about the elongation and contraction, and lastly we're going to go deep dive into creep, relaxation, and fatigue. So I would like to review again on our chapter's name. So our chapter name is the mechanical properties of material, which mean if we look at the material, so this is going to be the repeat stuff that we talked last time. We have in CE field, we're going to do a lot with concrete. Another one is going to be, if you have concrete, we're supposed to have steel, right? And for steel, we divide into many sections. Like for another one is structural steel. The second one is going to be the reinforcement steel. And maybe another one is going to be the wires. Most of the time we use it in PC. Okay. And next one is going to be the wood. And lastly, that normally we use in combination of the house construction is brick. Okay, I think you have done the brick test at F4 already, right? Last week, is it? Okay, so in the brick, you guys need to test what we call in every angle. For example, like we have flat wise, angle wise, and then in the vertical directions in order to see the capacity that it can resist. So if we look at TS standard, for TS standard, if we talk about the tensile steel again, we're going to find yield stress of the steel, ultimate stress of the steel, modulus of elasticity of the steel, and the percentage elongation that most of the time we use it in the testing. And for the CE material, the force that it's supposed to be subject to, for concrete, normally we test for the compression or compressive strain. Compressive strain. If we test for compressive strain, we're going to get FC prime. And then if we talk about steel, we're going to talk thing on tensile. Okay, so we're going to get the yield stress over here. Okay, this is just the repeat thing from last time. And the second one, after we test it from the lab, after we test the concrete, the steel, whatsoever, we're going to plot the thing called stress strain curve. Am I right? So after we test the stress strain curve, we're going to get something like this for the steel, and it's going to get like this for the concrete. So this one is concrete, this one is for steel, and we're going to plot it in order to find the mechanical properties of it. So mechanical property of it, I can basically just tell the strength of material itself. We call it mechanical properties of the material. The second one is going to be the Hooke's law. If you remember it correctly, Hooke's law, we're going to talk thing about sigma equal to E strain over here, which we allow you to use just only a small deformation in material. Okay, so Hooke's law, basically they want you to use the material capacity in between, or maybe half of the yielding, sigma y divided by 2. So most of the time it's in between. If you zoom in the curve, it's supposed to be between here to this one for the Hooke's law most of the time, which going to be a really small deformation going to occur after designing the members. Next is going to be the thing that we used to calculate it and were in the exam. These questions were in the exam from mechanics of material in question 3, I guess. And you guys need to do some plotting over here. So we have normally, and this one is going to be our written examination. Written exam. Here's, and then in the exam, I'm going to give you like something like this for the lower scale, like this, lower scale and upper scale. What you guys need to provide me is this one is stress strain curve. I'm going to provide you some force. If you remember it correctly, it can be tensile or compression. I may give you a column like this. I put some load, 2 point over here, and then I'm asking you what is the deformation of the bar, okay, or what is the deformation of the rod during the loading and after loading. Okay, in this question, I'm going to provide you the sigma y and e. So this one, I give you sigma y and e, and also the sigma PL. I think there's no sigma PL in the exam. I provide you this because to prevent the confusion, because sometime when you plot it in the papers, most of you like read it differently. So many of you gave me back in different result. So in order to avoid the difficulty for me, so just give you sigma y and e. So the answer is supposed to be the same for all of you guys. Okay. Lastly, the next one is going to be the understand the material due to creep. Creep basically is the long-term, can say that it's a long-term deformation of concrete. Okay, which mean your concrete may be changed in deformation for the long term, or maybe change in shape in long term. So that will be cause some dangers to your structures. So we're going to look at it later in detail. And another one is relaxation. Relaxation, as I said from last time, we have something called precast concrete, which we call precast wire. So we're going to talk about it later in maybe almost in the end of the slide. So I will explain you what is the relaxation in the tendon or in the PC wires. And lastly, is going to be fatigue. From last time, I explained you a lot about fatigue, which means basically we're not gonna apply the full capacity to the material, but we're going to apply some load to the material, and then we're going to release it back and then count it as the cycle, stress and its cycle Sn. Okay, so we're going to see it later in the end of almost in the end of the class. Okay, all right, just go quick to the example. So this one is similar to chapter 3, chapter 4 in McMed. So the question basically asks, one is the modulus of elasticity. The second one is proportional load. It's not proportional stress. So it's going to be PPL over here. And C, they said that if there's a rod with a diameter of 12.0 millimeters and the length over here is not 50, it's 500 millimeters. And then it's subject to the tensile force, which means they pull it 500 MPa, and then what is the elongation and its length. So they would like to know what is the elongation during the pulling. Okay. Okay. And then if the stress is released, what is the permanent set and its final length? So things are really similar to what we discussed last time. Starting off with the modulus of elasticity. So if you remember it, you can see that we have the PL point, which is the last point of the curve at the linear region, which is this point. And then we just like plot this to the y-axis, and then we're going to get the sigma PL directly, and then we're going to get the strain PL directly. So in order to get the E approximate over here, or the modulus of elasticity in approximate, we're going to use the slope over here, which is equal to delta sigma over delta strain over here. And then we just give the last point over here 280s, and then the strain over here equal to 0.001. Okay. So do you know why we read the bottom scale, not the upper scale? Why don't we read the upper scale? You can see we have a black one and then the sky blue one. Because of the lower scale, it's really easy to read the data in the linear. So they just like reduce the scale from the big one. Basically, this curve is going to be, if I draw it in one scale, like in the big scale over here, it's going to be like this. Going to be really small like this, like this, and like this. So it's really hard to get the point during this one. So that's why it's just separated and then separate it into the lower scale over here. Okay, lower curve for the lower scale. Okay, in the examination, please do not put this one, otherwise you're going to mess everything. Okay, so they would like to find the PL after we know the E approximate over here already. So basically this one is the sigma PL, and then A is the area of the bar, which is equal to pi over 4 the squares. And then we just input everything here. This one is the PL. Okay, stress PL. Just put it in here. Stress equal to force over area. So if I would like to find force, going to be equal to stress A over here. So that's why I put it here. And then we're going to get the force in 31.67. Okay, as we would like to find the proportional load. C is going to be the elongation of the rod. They said that what if I pull it 500 megapascal? What happened? So if I pull it 500 megapascal over here, and then I know that the strain, the yielding stress over here, it's larger. This one is larger than the yielding stress. So can you tell me the behavior of material? Is it linear, or is it elastic or plastic? If this one is larger than yielding stress, plastic, right? So if it's larger, so we call it plastic. So what is the definition of plastic in this material? So after I pull it, will it come back to the same shape or no? No, right? So because of the energy of the material itself, so it can come back a little bit of the length, but it's going to give you some permanent length. Okay, so let's see, after we pull it, when it's plastic, what should we do over here to get strain is to plot from the graph only. We need to plot from the graph only. We cannot use Hooke's law in order to find it because it's beyond the elastic region. So after I plot it into the graph over here, the stress strain curve, I'm going to get it 0.08, and I just place it here, which means if I would like to find the deformation, so the deformation over here, you guys may be familiar with this. strain equal to deformation over L. So it's come from the same equation. So it's going to be deformation equal to strain multiplied by L. We know that L equal to 500 millimeters, and then strain is the one that we plot from the curve over here, and it's equal to 40 millimeters. And then the rod length is now at 540 millimeters, which means if I go back here, when I apply 500 over here, extend a little bit, extend a little bit. Now the length over here is 540, okay, millimeters. And then the next question they ask, what is the permanent set? If the stress is released, what is the permanent set and its final length? Okay. As we discussed recently, we said that the material itself is going to recover some length, okay, which is not 100%. But we don't know the distance of the recovery, so that's why we need to find the elastic recovery first. So this one is going to be the strain recovery. So the strain recovery is going to be stress of 500 megapascal divided by its Young modulus. Okay, and then we're going to get it equal to 0.001786 millimeters by millimeters. And then if I would like to find the amount of the recovery, so I can just length of the recovery over here equal to similar formulas, which is strain recovery multiplied with L, which is the length of the sample, and then I'm going to get it equal to 0.893. Okay, and next we're going to find their permanent set, which means if I pull it, it's going to extend 540. When I release it, what happened? It's going to short take both sides equal to 0.893, which means there will be a huge permanent set on this material. Okay, so we're going to use the strain from the graph minus the strain recovery. Okay, so we're going to get it equal to the strain permanent. Okay, and then the permanent elongation is going to be the strain permanent multiplied with L over here, which is the length of the sample. Okay, after I release it, it's going to remain 539.1, which means if I remove the load here, everything set to 0. This one from 540 over here, it's going to come back a little bit, just only a small amount of it. So it come back to 539.1. Okay, which means this one is going to be another stage of the material. Okay. All right, so the second example, it's going to be similar. Okay, but Achansy Dichai simulate this according to the bearing frame like this. For example, if I have if I consider this column, okay, if I consider this column, you can see that the load transfer from the roof to the column from both sides. Okay, this one too. Okay, for example, we neglect this one. Basically, it's supposed to be from three sides, but for example, if we neglect it, okay, after we know the problem statement, we just convert it into free body diagram as shown in the bottom over here. Okay, for the x-axis, you can see that P1, which is from the roof over here, we have 2 P1 from both beam. Okay, P1 equal to 200 kilonewton. This one is also 200 kilonewton. So the reaction of this is going to be FAB. It's going to be to P1, which is equal to 400 kilonewton. Okay, so another one is P2. P2 over here, which P2 has a really high load equal to 2400 kilonewton, because when this is on the roof, so the load is smaller than floor. Okay, because we're going to use the function over here at the floor, and then on the roof we just use it to support the roofing material only. Okay, so that's why the load are quite different from 200 to 2400. So this one is going to be 2400 kilonewton. This one similar thing, 2400 kilonewtons over here. So the reaction, we're going to have another one from FAB, which is 400. So the reaction of the column BC is going to be PBC equal to 2P2 plus FAB. So it's going to be 400 plus 2 multiplied with 2400, which means it's equal to 5200 kilonewton over here. All right, so to calculate it, everything going to follow the same step. We have area of the column AB and area of the column BC over here. And then what we can calculate first is the stress AB. Stress AB is going to be PAB over AAB over here. After we calculate it, it's less than yielding stress. Our yielding stress is 250. So this one is 250. So when it's less than, it's linear elastic. It's elastic, right? It's in elastic region. So when we release the load, everything come back to the same length. And then for BC, we have PBC divided with BC, and then this one is larger than yielding stress, which is inelastic. And this one, we just consider it that it's in plastic region. Okay, which means our column BC going to deform some shape, which cannot become back later. Okay, so the question is, Achan, we know that sigma is equal to E strain, right? Am I right? And then we know that sigma equal to P over A, and then E is going to maintain the same thing, and deformation, the strain is going to be deformation over L. And then I'm going to find deformation equal to PL over EA over here. So if the question asked for AC, so it's really easy for me to find the deformation of AC. Am I right? Can I use this equation? Can I use it? Can I use it? Can you guess? I can't use it, right? So it's wrong. I cannot use it. Because of what? If you look at this one carefully, from Professor Hook, this one we can use when it's in linear elastic behavior, which means it's can be used when your material is below sigma y only. But if you would like to consider for both AC, which means this one, can this one use the Hooke's law? AB, can I use it for Hooke's law? Yep. For BC, can I use it? No, right? So what should I do with BC? I need to plot from stress strain curve in order to find strain in plastic. Okay, am I right? Okay, so we have one agreement which sigma equal to E strain can be used to find the displacement only for the material that is in linear elastic behaviors only. Okay, if it's beyond linear region, you cannot use it. Use stress strain curve instead of it. Okay, all right, now we have the agreement that we're going to use this one from sigma BC, and then we plot it in stress strain curve. After that, I got the deformation from this curve equal to 0.0108 millimeters by millimeters. So the final one that we can use is going to be this. Okay, this one is the correct equation. Okay, this one is elastic and this one is plastic. Again, elastic, use Hooke's law, Professor Hooke's law, and then this one use from the graph only. Okay, and then just substitute everything. We know that our column length is 4 meters for both. This one is L 4 meters, and this one is P, this one is A, and this one is E. Okay, this one is strain BC from the graph. Okay. All right. After we put everything together, we're going to get a deformation of 44.07. All right. Next is what if we release all the load? Okay. What happened? Again, for the linear elastic, everything is going to come back to the same shape when we release it. But the problem occurs just only for the material that is in the plastic region. So in the plastic region, again, we know that the column BC is in plastic region. What we need to find is we would like to know what's the length that it can recover back. To find the length, first of all, we need to find the strain recover first. It's going to be stress BC over E. E we know, stress BC we know, so we're going to get the strain recovery equal to 0.00175 millimeters by millimeters. So if I would like to find the recover length, so it's going to be 4 meters or 4,000 millimeters multiplied with the 0.00175 over here. I'm going to get something in millimeters here. Okay, and the remain over here, if we look at the curve, the strain remain, basically this one is the strain permanence, or we can call it strain remain. It's the same thing. So the strain remain here is going to be strain BC minus the strain recovery of BC. Then it is 0.0108 minus 0.00175. Just subtract it, and then you're going to get 0.00905, which is this one, the strain remain or the strain permanent. Multiply with the length, which means if you put the load, it's going to compress the column to get the deformation or contraction to 44.07. But when you release the load, your column is going to recover only this deformation, and then what it lost in length is 36 millimeters. Okay, so that's what I want to mention, and it will be in your midterm exam, of course. Okay, please practice it. If we have enough time, we're going to practice the problem 2.1 and 2.2 later. Okay, until this point, do you guys have any questions so far about that? So if I conclude in short, what you guys need to do is draw a correct free body diagram, find P1 and find P2. Next, find stress. I provide you the area, you find stress for both, and then check which rod is going to resist the higher load than sigma y, and then just tell me which one is plastic, which one is elastic, and then you guys need to find the sigma recovers, and then find the length of the recover, and then find the permanent length, and then just answer it. It's really simple. Next, one material that really close to us, but we may not see this much because it's under the bridge. Okay, when we construct the bridge, we cannot use the steel plate in order to put it. For example, if we don't have the bearing pad over here, we don't have here. So when you brake your car or the motorcycle on the bridge, it's going to produce some shear stress, okay, to your support. So if you use the steel itself, okay, which means it absorbs less energy than the bearing pad, which means it's going to provide a really small resistance in shear, because the energy when you brake is too light, right? So the engineers are really genius, and then they just invent this thing called bridge bearing pad, which is the connection between the cross beam. Basically, cross beam connect with the here, over here, and then they just put the bearing pad over here in order to change the support from fixed to just only. Can you guess what is this support? Is it pin, fix, or roller? It's supposed to be roller, right? Because when you put it here, it's going to resist this one. Okay. Theoretically, it's going to resist the vertical load only, which is the force in one direction. Okay, like this. Like this. We zoom in. Like this. Yes. Okay, transfer back to the cross beam, and we have shear resistance like this. Okay. But in reality, when you break it, it's going to produce some shear stress, okay, to the bearing pad, and the bearing pad still resists the axial load. So from this, we can find, from this, we can think about two graphs. One is the stress strain curve, stress strain curve, stress strain curve is for the actual forces, and then another one is the shear stress and shear strain. So you guys have learned about torsion already, right? Is that torsion or fatigue that you learn on the second level? Torsion, right? Was that torsion or fatigue in the lab? Torsion, right? Okay, so that's good because it related to our class today. So let's see next. All right, so for the bridge bearing pad, we need to follow the AASHTO M251 over here to test it. So you can see that the material behavior itself when it's subject to the horizontal load, which is the load in x-axis over here. When you put the bridge, the load on top of the bearing pad, it's going to produce the compressive force, and compressive stress. And then when we put the horizontal force, it's going to produce some shear stress, which is our angle over here. Okay, shear strain over here, right? So this bearing pad can absorb. You need to test. The machine is supposed to be able to apply the force up to 1,000 ton and the horizontal force up to 60 ton. Okay, over here. All right. Come back to here again. If you see this, you may flash back to your lab. Okay, because in your lab you're going to test just only these two sample. So we have one is iron, another one is cast iron. Am I right? So the procedure to test this, what you guys need to do is you're gonna need to measure the diameters, and then you can just convert this into R equal to D over 2. Okay, and then measure the length L. This is the initial parameters that you can measure. So you have L and then you have R. Okay, but in the final result, what we would like to have just only the shear strain and shear stress. Okay, and then you guys plot something look like this and go down like this, and then we're going to find for the G, which is the shear stress modulus of shear modulus of elasticity. Okay, so if we flash back really quick to the procedures, what you guys need to do is you guys put the sample here. Am I right? And then what should we do after this? Put the sample and then apply some load. Okay, and then we're going to get T. And then what is another parameters that we can read from the machine? We can read force, and another one is the angle. Okay, so we can read the angle. But from here, how can we compute for the shear stress and shear strain? Do you still remember how to get it? Basically, shear stress you can calculate equal to T and then R divided with the J, which is the polar moment of inertia over here. So if you know that polar moment of inertia, polar moment of inertia is going to be equal to pi r power 4 divided with 2. Okay, so if you rearrange the equation, you're going to get equal to 2t over pi r over 3. So you use this to find the shear stress. So for shear stress, you can find by having one is the torque that you rotate the force, and then another one is from the material diameters. Okay, divided by 2, you're going to get it equal to its radius. The second one is the angle of the shear. So when you apply the torque, or when you test for the torsion, you're going to apply the force like this, T. Okay, so what happened to the sample is the inner grain from the middle over here is going to rotate into some, the shear strain is going to occur here. Okay, and the shear strain is going to subject to the length L, which you already measured at the start. And then when you rotate the shaft over here, you can see that there will be some parameters can be measured, which is the angle over here. And then we know that the distance from here to the surface of the material is r. So when you try to move this, there will be some t occurs and this one occurs. So when the angle occurs, which means the shear strain also occurs in the sample. So that's why we going to put it together equal to alpha VR multiplied with the L and then shear strain. So to get it, it's going to be shear strain equal to R divided by L. Okay, so this one from material, this one from material, and this one from measurement. Just to brief it in short again. Okay, and then we just plot it point by point, and we're going to calculate for the final one is going to be the t value. Okay, similar thing as what we have taught. So this one is going to be the thing that we plot in the lab. So we find g, we find the proportional limit of shear stress, we find the ultimate shear stress, and then we find the fractures of the shear stress over here. Okay, all right, next one is going to be the behavior. So you can see the failure of the steel and cast iron under torsion. So it different, this one is different from actual stress. Okay, the actual stress is the one that we talked last week. So I'm going to include it again in here. When it is a ductile material, for example, like steel, ductile material, then we apply torsion, and then the failure of the torsion is going to be in the angle of 90 degree over here. After that, if they ask you what is the force that make it fail into 90 degree, you guys need to tell that it failed by shear stress over here, which means for the ductile material, you apply torsion force, it's going to fail 90 degree like this to the surface, and then it fell by shear stress. Okay, the second one for the brittle material, so this one is brittle, we apply torsion, and then the failure angle is 45 degree and it's failed by tensile. Okay, so I may ask you if the material subjected to, if the brittle material subjected to the torsion, what is the failure mechanism? So you need to answer the tensile stress. Okay, due to what force that make it failure? So it failed by tensile stress. Okay, and then we have another one, which is the actual force. So for the actual, this one is the ductile. I can just do thing the same from previous lectures. Ductile, if I apply the actual force, it can be compression or tension. It's going to produce the angle of 45 failures for the steel, 45 degree, and then it failed by shear stress. Shear stress, because it failed by dissimilar image. And another one is going to be the brittle material, brittle and we apply actual, and then it failed in 90 degree, and then it failed by axial stress. Okay, so this is the conclusion of the failures. All right, another one is the Poisson ratio. So Poisson ratio, in short, V is going to be minus lateral strain divided with the axial strain. So the lateral strain, we can write the symbol as the strain lat and strain long over here. Okay, so this one you need to remember. They will be in the exam, of course. And for the tensile members, when you try to pull it like rubbers, for example, if you pull it like this, what happened is there will be some changes in diameter, which the diameters D0 is going to be larger than DF. Okay, when the diameter of the original larger than DF, when we find the deformation over here, so it's going to stick with minus. Okay, so if one axis is going to stick with minus, which means if we going to multiply together in the big equation of Poisson ratio, so this one is going to be positive, which means Poisson ratio is a unitless parameter which has value in positive. Okay, so if you provide me Poisson ratio in negative, so you're wrong. Okay, so please recheck it. For the compression member, similar thing. For example, for the compression member, when you compress it, the diameters of the member, that's going to increase. Okay, when it increase, what happened is df larger than d0. But if you would like to find the deformation over here, it's going to be positive. But the length itself for the longitudinal direction, this one is going to be the lf going to be smaller than L0, which means the deformation over here is going to stick with minus. Okay, so if you put minus, even though you would like to put it here or you put it here, it's going to be the same, but one side supposed to be minus. And then everyone just agree that okay, we just put it at the lateral. Okay, so that's why we stick the minus sign with the lateral strain. Okay, so similar to your lab number 2. Okay, this one, just the example how to test it. Grab top and bottom and then try to stretch it. You can see that the L over here change. This one is LF, L0 over here. Next is going to be the example, but this one is not gonna be in the exam. Okay, so it's similar to what you have test in the lab. So we have stress, and then we calculate strain. After that, but this one is going to be the reverse calculation from the lab. So you test to find Poisson ratio, but this one, if you know Poisson ratio, so you can find the deformation in each axis by your own. Okay. All right. Come to another point, which is called pre-stress. Okay. If we divide this word into two terms, we have one is pre, and then we have another one is stress. So the equation of the normal stress is going to be P over A. Okay, so the pre-stress, which means we apply some stress before we cast the sample. Okay, for example, in this beam, this girder, like this. Okay, I have this girder like this. Okay. So in order to make a pre-stressed concrete, you need to pull the PC wire first, which PC wire has a really high tensile force, which normally for the sigma y for the normal steel it's about 400 MPa. But for the PC wire, the sigma y can be larger than 1 to 0 megapascal. It's about like 3 times higher. Okay, we call it high strength steel. Okay, and the concrete itself for the normal FC prime equal to about like 210 KSC or 21 MPa, 20 MPa, 25 MPa. So it's lower than it's normal for house construction, but for the precast, we need to use a really high FC prime. It can be larger or equal 40 MPa, almost 2 times. Okay, so let me explain something about the pre-stress. Okay, can someone here come to the front? Help me putting some wire. You have, can someone come to the front? Let me pull this wire. Okay, right. You pull it here. So the pre-stress basically. It's okay. It's okay. It's okay. So basically, if this one is a normal steel, right? If we put some load over here, like the normal steel means the normal beam, the normal concrete, and the steel. If we put it here like this, it's going to deform a little bit. Okay, which means that's why we put some allowable deformation equal to L divided by 360 for what we call to not let the beam deform until it provides some stress to the brick. And L equal to L divided by 240 for the roofing beam. But this is the behavior of the real RC, which is we just put the steel like this, and then we put load, and then you're going to have this. Okay, but for the pre-stress like this, which means you pull it first like this, and then we put it here, so nothing happening. Okay, which means we pull the steel first, and then we can just hand whatever load we can. So this one we call it pre-stress. But the thing is like this: when you try to pull like this, which means normally you and I are machine, so we just like pull the stress over here. We pull about like 80 megapascal of the yielding, and then just put it in here. And then after the concrete harden, for example, if 100 megapascal is what I was pulling, right? 100. We have sigma y equal to 100, and then you and I pull 80, which means right now we pull 80. Do you know what happened after the concrete hardened? I just cut it here and then cut it. So, do you think what happened next is the wire over here trying to go back to the same shape? Okay, which means this wire is going to be the stress to the concrete like that. You got what I mean, right? So if I pull it like this, nothing happened. But after I cut it, that's why we call it pre-stress. Right. So if you look at the image over here, thank you so much. If you look at the image like over here, you can see that there is some PC wire here. After they cut it, the PC is going to is trying to go back to the same shape, which follow the Hooke's law, right? Because the Hooke's law is going to be like this. like this. And then we have, for example, if we have sigma y is over here, we're going to use just only 0.8 of the sigma y. Okay, so when we try to pull it, it's going to be somewhere between here, for example, 0.8 sigma y. So that's when I and him pulling the steel. Okay, when I cut it, what happened? It's similar to loading and unloading that we just talked. So when it's in linear region, after we apply, after I release the load, what happened? The strength trying to go back. So there will be some stress going to push to the surface of the concrete over here. You got this concept, right? So when we pull it and then after we cut it, the material trying to go back to its original shape, okay, which has no stress. But we have the concrete over here in order to hold the stress inside the concrete. So if the concrete over here is the low strength concrete, what do you think it's going to happen? It's going to break, right? Because if you pull this 0.8 by the machine, after you catch it, release it, this one is going to go back, trying to go back at 0.8 sigma y. Okay, if the concrete surface over here has the strength less than 0.8 sigma y, so this concrete cap at the surface going to break or going to explode. Okay, that's the concept of pre-stress. Okay, all right, so to conclude in short, pre-stress is the method in engineering that we use the material capacity in order to reverse engineering to make it has almost zero deformation to the material by combining concrete and the high strength steel together. Okay, so that's we call pre-stressed concrete. All right, so if you look at this image, it also can be clear. So this is the normal unstressed beam, which is the normal RC beam, like this. Okay, so when we have the reinforcement inside, and then we put some dead load, or this one is the wall load, right? We have wall load, and then it's going to deform as normal. So it's going to provide you some deflection, but we cannot see by our eye, okay, because it's really small. And then this is the pre-stressed steel or high strength steel that we're going to pull it out first, as me and him trying to pull this. Okay, pull it first, and then I cast the concrete in here, and then what happened next is I cut the steel here. When I cut the steel here, there will be some force pushing to the surface of the concrete, and then the concrete trying to reverse the deformation according to the stress, the pre-stress. Okay, actually this beam is going to, if you zoom in, it's going to deform like this, but we cannot see by our eye. Okay, but it's going to look like this. Okay, and then when we put some force, which means this one is going to be back to 0 0 only, it cannot be deflect down. Okay, that's we call the pre-stress concrete. Next is going to be creep. So creep is one topic that going to be in our exam. So creep is the material failures due to permanent deformation and continuously increase. So most of the time it's in concrete only, which has cement waters, we have sand and stone, or just call it gravel. And then another component that's in concrete is the air. Okay, so to explain this, let's see these figures. Oh, some figures disappear over here. So this one is RC beam, and then this is the decoration, which is the wall over here, and then there will be some force dragging down like this. Okay, in the first like few years, there's going to be nothing happen. It's like your hand hanging like this. Okay, but at some point of the time the creep occurs, the beam is trying to deflect down like this, which means it's going to produce some void or cracking at this point. Okay, so when the creep happen, for example, normally we use to calculate the surface area equal to its full capacity, right? The full surface area. But when the creep happen, some area cannot be included in the resistance capacity. It may be reduce its capacity to 80%, and then at some time reduce to 70%, 60%, until the beam cannot resist the force and then it fails. Okay, so this is how the creep happen. This one also, but this one is still okay because of the reinforcement have holding the shape of the concrete. It looks scary, but it's functional, so there's nothing happen. But this one caused by the creep of the RC. Okay, reinforcement concrete. Next topic is the relaxation. So the relaxation itself is the term from the PC wire over here, which is the stress is trying to reduce from 0.8 down to 0.6 sigma y. Okay, for example, me and him trying to put it 80 inside the concrete. You know that the concrete is so good, right? So it can hold the wire itself like this. But the inner grain itself, for example, if this one is concrete, my hand is concrete, and this one is the PCY. The inner grain itself, when we pull it 80, 0.8 sigma y, it's going to produce some relaxation inside. So the grain from the PC wire itself try to adjust itself by natural. Okay, so when we pull it 80, when time pass, it trying to adjust itself down to about 0.6 sigma y. Okay, which means for long duration until the structure cannot be performed, intend to function as designed. So we call it relaxation. Similarly, so when we pull it, it's okay when we have the fixed support. But when we cut it, the force trying to push to the concrete surface like this, okay, and the wire itself trying to relax. Okay, at some point of the time, it won't be functional for the wire. Okay, that's we call the relaxation. Next one is fatigue. Fatigue is one of the closest. You may not like notice it, but it's really close to you. For example, as I explained last time, like you drive on a motor on a road, you drive it on the bridge, or you may use your fans during clipping. You can see that it's going to rotate, and then you click number 0 to stop it. And then if in the morning you are feeling hot, and then you just like click it again to make it rotate. So it's similar thing for the fatigue. Fatigue is the force that we're going to apply and then release the load. Okay. For example, if you learn in the lab, so we have the machine like this. This one is the machine box, and then you put the sample out like this. Okay. This is going to be your sample. And then the machine itself going to push the force P over here. Okay. So the machine is going to work like this. So it's going to push and then stop. And then push and then stop repeatedly. Okay. So if I would like to draw some free body diagram, and I have this one is the distance L. If I cut it down to the small piece over here, I have P over here, upward. If I would like to balance it for the internal force, I'm going to have the V over here, and then I'm going to have the balancing moment, which is M over here equal to P multiplied with L. Okay, if I would like to find the bending stress, it's going to be M multiplied with Y over I over here. And I for the cross section over here, it's going to be it's going to be pi R over 4 over 4. Okay, if I substitute in here, basically Y over here is the radius. So just put MR over pi R 4 over 4. So we rearrange the equation, we're going to get 4M over pi R power 3 over here. Okay. And then what is the stress over here? Okay. If you remember from mechanics of material, if we have the surface over here, okay, when you have the P pulling up like this, there will be some compression force to your section. So this one is your sample, right? And then you calculate the stress for the sample. And then there will be some stress compression force over here. And then there will be some tensile force occurs over here. Okay, have T, which means if you apply over here, you try to pull it, boop, release, pull up, release, which means this one is going to experience the tensile at this point, right? At this bottom. Just circle it big like this. At this area, go to experience repeat thing tensile stress, which means the material no need to fail by press it until it fails. Sometimes if you apply just only 50% of the sigma over here, the stress over here, but you apply it and then you stop, you apply it and you stop in cycle, apply, stop, which means loading, unloading, loading, unloading at some cycle, the material is going to fail. Okay, and for the fatigue, material is going to fail in as brittle material. Okay, so it is its behaviors. For example, like the airplane wing. Okay, when you fly, the airplane is going to experience the uplift force. Okay, when you landing, the wing of the airplane is going to experience zero force, which means when you go up, you're loading, and when you go down, you're going to be unloading the force to the airplane wing in the same behaviors. Okay, for example, if you design the mobile crane inside the factory, So you also need to consider about the fatigue too, because you're going to hang some thing, go over here, which means you load here, loading here, you load here, and then over here, hang over here, and then drop here. So over here is unloading. So it's going to be repeat, and then at some point it can be failed. Okay. Similarly to the brick girder, when we design it, we also need to consider about the fatigue. But let's see how we convert the data from the fatigue testing. So the fatigue testing, we're going to start with the stress and number of cycle. Okay, so you can see that in x-axis is cycle to failures or number of cycle, and in y-axis this is the stress. To test it, we're going to apply the ratio of the stress. For example, I test at the lab and then I get stress ultimate equal to 100 megapascal, and then I'm trying to apply 0.5 stress U as my stress number 1 for fatigue test, 0.6 stress U for the stress number 2 for my second test, 0.7 stress U equal to my third test, 0.8 stress U equal to sigma 4 is my fourth test. Depends on your application. You can see that this is the number of loading and unloading, which is the cycle of the material, which means the more stress you apply, to the sample, the lower cycle you get. Okay, which means if you apply the low stress, for example, at 600 megapascal over here, you're going to get more cycle over here. Okay, this is how we convert the test. For example, I test this one as my sigma 1, sigma 4, just for example, sigma 3, and this one is 500 as my sigma 2, and then at this point is my sigma 1, which is about 0.5 sigma U. The thing that happened with 0.5 sigma U of my steel alloy is it's not gonna fail. I test it in this machine. I just like push, pull for 2 days. Nothing happened to it. So that point we call it as the endurance limits. Okay, the endurance limits means the material is not gonna fail by loading and unloading. Okay, so it's not gonna fail by loading and unloading. It's just like whatever you push and then remove the load, and then that's it. Nothing happened to it if you apply just only 0.5 stress ultimate. Okay, so we call that point as the endurance limit. So it's going to have the an infinite life, which means there's no cycle to it. You can apply millions time, 2 million times, it's still okay. So it's approximate 0.5 of the ultimate. That's why when we calculate the structural members in our CE, most of the time we limit the structure to be at 0.5 yielding, which mean, what does it mean? You know that yielding is lower than ultimate, right? So it's going to be 0.5 below ultimate, 0.5 of the ultimate, which means if we design, we use just only 0.5 of the yielding, so it's really far from the fatigue. So it cannot be happen easily to our structures. Okay, if it's not specifically designed in the as the mobile crane like this. Okay, if you design for a mobile crane like this, we need to consider about the fatigue. But if it's not, no need to think about it. If it's just like the normal structures as we design. Okay, so that's the inherent limit. So the point that sample will not be failed by fatigue. Okay, next one is really interesting, like the non-ferrous metal such as aluminum under fatigue. The problem is they cannot predict the number of cycle. Okay, which means for example, like the airplane wing, we don't know what is the exactly number of cycle that cause it to fail. Okay, but they can test it for the fatigue, but they don't have the endurance limits. Okay, when they don't have the endurance limits, which means they need to always check it for the airplane wing, for example, right? And then they're going to set the really high error point like this. We just like call it like a factor of safety of the failure cycle at the minimum over here. Okay, and then for example at this point we're going to get it about like 4, for example, from this curve, power 7 cycle. But we're not going to use this. We're going to divide by half more because we cannot predict. Okay, so we just like okay, just divide by 2 for the safety. So I'm not gonna risk their life by just like the testing over here. Okay, that's a really hard part for the aluminum or the non-ferrous metal in fatigue resistant. Okay, and this is it failures. If I conclude in short for the fatigue, it's just the loss of resistant surface. For example, if you calculate the stress, okay, it's going to be P over A, right? Stress, the resistance, the strength from material. But when fatigue occurs, you know what happened? It starts by losing its resistance, surface, which means at the start it's going to be all resistant surface over here. Okay, but at some point after it experiences the fatigue, it's going to be poop, and then poop, the resistant surface disappear when the crack open, and then at another point disappear, and another point disappear like this, and then when the remaining surface cannot resist the load, it fails as the brittle material. Okay, it just like pop and then fail. Okay, so this is fatigue, and we are in off chapter 4. Okay, all right, so we're going to have a really short quiz for today. So you guys need to be in the group together. How many? Group A? Group A. How many of you? Just only 2. Okay, please sit in the group and then try to solve for the problem number 2.1 and 2.2.